So here is our first example for formulating a linear programming problem. You work for a clothing manufacturer as a shop floor supervisor. One of your responsibilities is to help determine the weekly production quantities for two products produced in your factory, men's shirts and men's pajamas. There are two major steps to making both of these products. You have to cut the material, and second, you have to sew it. Over the next week, you have 280 hours available in the sewing department and 450 hours available in the cutting department. Each shirt takes 1 hour of sewing and 90 minutes of cutting. Each pair of PJs takes 45 minutes of sewing and 2 hours of cutting. You estimate that each shirt produced will add $4 in profit, and each pair of PJs will add $3 in profit. Formulate the LP. So again, here I do not want you to try to figure out how many of each you need to make. I want you to abstract the problem and formulate it. I want you to tease out different parts of it. So what are our decision variables? What would be the objective function? What would be the constraints? Things like that. So this is called a product mix because we're deciding how many of each product to have in our weekly production cycle, and so we'll go from there. So on the next here we have the way I want you to formulate it. Right? So we have let, that's where the decision variables go. And then I want you to also have, I tell you it's a maximization problem, that's the max. And then S period, T period stands for subject to, and the constraints go down below that. So here we need to define two decision variables, one for the shirts that we want to produce, and the second one we need for the pajamas. So I'm going to say let x1 equal number of shirts to produce next week. So we should be that specific, right? We have, because our hours of sewing and cutting were given to us for next week. So we can't make any decisions past that. And then we have x2 is the number of pajamas to produce next week. Right? So we want to maximize. What are we going to maximize here? We're going to be maximizing total profit because that's what was given to us. How much profit do we make for shirts? $4. So we would make 4 times x1 dollars in profit, plus, that's the additivity assumption coming in, $3 for each pair of PJs, so 3x2. Right. We're not selling anything else, so we're not getting profit from anything else. Subject to constraints. So here, let's start with cutting. We have to cut the stuff before we can sew it. We had a total of 450 hours of cutting. And so I want you to attach a word description and braces next to it. So this is cutting hours. All right. We cannot use more than what we have, the 450, so we need an inequality of less than or equal to. So the right-hand side of this equation, inequality, is a number. The left-hand side is going to contain variables with the coefficients in front. So for each shirt I cut, how long does it take? It said 90 minutes. Well, I need to convert that to hours because the right-hand side is hours. So I have 1.5, make sure you can see that period there, x1, and each pair of PJs takes 2 hours of cutting, so 2x2. So that'll make sure that I stay under the 450 that we have. The second resource that we had was sewing. We had 280 hours of sewing available. So this is sewing hours. And again, I'm going to stay under that, so we use a less than or equal to. It takes 1 hour to sew a shirt. I'm going to go ahead and put a coefficient 1 in front of the x1, just so you know where that's coming from. In the following problems, I will not do that, right? But we could leave it out. It's implicit if it's a 1, if it's left out. And it takes 45 minutes to sew a pair of PJs. So we need to convert 45 minutes to hours. That's 3/4 of an hour. But you probably like decimals better. So that's 0.75x2. Right. So do we have any other kind of constraints that need to go into this? I don't think so. I mean, we only had 2 main resources, sewing and cutting, so I think we're taking care of both of those. What we do have to make sure is that x1 is greater than or equal to 0 and x2 is greater than or equal to 0. And both of those are non-negativity. Right? Those are the bounds that we were talking about before. These top 2 right here are structural constraints. You can almost read my handwriting there. That's a C. Right? They define the structure of the problem. These down here are bounds. They restrict us to the first quadrant of the Cartesian plane, right? The structural ones define the resources that are going on. So there's our first formulation. We're not going to solve it right now. We will solve it later. But again, here I just want you to practice actually taking a word problem and putting it into symbols, and then making sure we capture everything that we need.